Section 15.6 deals with integration. And the integration under the peak quantifies the relative number of protons giving rise to a signal. So what this means is that a computer is actually going to calculate the area of each peak, and it's going to represent that either with a step curve or with providing just an integration value, and those are shown down here in red. So again, what this means is that the computer is actually going to calculate the amount of area that's under all the peaks in this signal, and then it'll do it here. Now I'm not going to do it for all of these, but that's what it's doing. It's calculating the area that's under there. Now it's not giving you any kind of unit, but it's giving you a relative amount of area for each one of these four signals that's shown in this proton NMR spectrum. And then it gives you the integration values. So we have 27 for this one here, and then we have 40.2, so on and so forth. So again, this doesn't mean that we have 27 protons and 40.2 protons, because we can't have a fraction of a proton. It's important that you understand that these integration values are the relative number of protons giving rise to a signal. When you're processing your NMR spectrum on your computer, the computer operator can set one of the peaks to a whole number and let it represent a number of protons. So say, for example, we said, okay, we'll take 27. If we divide that by 27.0, we end up with 1. Well, we can do the same exercise with the other three integration values. And look what happens when I divide every one of these integration values by the lowest integration value. Now the math is already done for me. I end up with these numbers: 1, 1.48, 1.05, 1.56. Now you can see that I don't end up with whole numbers for all of these. For example, I can't have 1.48 and 1.56 and 1.05 protons. But what would happen if I was to multiply all of these by 2? Now I end up with integration values which are all much closer to whole numbers. So this kind of looks like 2 and 3 and 2 and 3 to me. So it's important that you understand that when you're calculating your relative numbers of protons, you try to get to the nearest whole number. You're never going to get 2.00, 3.00, 2.00, and 3.00, but you can see that these values are very close to 2 and 3 and 2 and 3. The conclusion that we can make from this is that the relative numbers of protons represented by these four signals are 2 to 3 to 2 to 3. So it doesn't necessarily mean that this is 2 protons, this is 3 protons, this is 2 protons, this is 3 protons, because remember, these are relative numbers. It could also represent 4 protons and 6 protons and 4 protons and 6 protons. So when you're solving the integration for the relative number of protons, usually you use it in conjunction with a molecular formula, and you multiply the relative number of protons by some kind of factor, so the total number of protons in the integration will equal the total number of protons in the molecular formula. Again, the integrations are relative quantities rather than an absolute count of the number of protons. Symmetry can also affect integrations. So if we take a look at this compound here, this is called 3-pentanone, this ketone that's shown right here. It says 3-pentanone has 2 kinds of protons, and that's because of the symmetry that runs through the molecule here. So that means that these 2 methylenes are chemically equivalent, as are the 2 methyl groups. So the 6 protons in those 2 methyl groups, those are going to be chemically equivalent as well. So if I was to measure the relative integration value for the 2 signals that I would get in this proton NMR spectrum, the ratio of those 2 signals would be 2 to 3. Therefore, the relative integrations don't represent 2 protons and 3 protons. They would represent 4 protons and 6 protons. And how did I get that? I had to multiply by 2.